All right. Did y'all have a good weekend? Yeah?
No.
All right, so administratively, our exam is next week on Thursday, and it will cover up to whatever we get to this week. So whatever we finish with on Thursday will be on the test. I don't know how far we're going to get. So today we are going to start definite integrals and probably get into improper integrals today as well. And then we'll just see how far along we get. The jury duty thing, y'all got that email? Yeah. Okay, so they're still doing the Zoom protocol. So I had to do a Zoom session yesterday morning, and there's like 600 people in there, and then they filter that down to people, and then those people have to show up for court, and I got picked. So I'm gonna go tomorrow to the courthouse, and I'll be there from 9 a.m. to question mark, and I won't be here for office hours tomorrow. So that's what I'm just letting you know. And then hopefully I won't get picked to actually sit on a jury. I'm gonna talk to the judge tomorrow, because
something kind of blatantly out there that'll get you thrown out.
yeah, I could go in there with, a pickaxe and just like burn them,
Just saying that I didn't think it was.
You just hit my camera, man. Yes, you did. It's all right. I'll adjust it. Yeah, so I actually think I'm going to talk to the judge, because if you're a college student, you get out of jury duty. But if you're a professor, you don't. But then that impacts every student, so it doesn't make sense. So I'm going to see if I can talk to the judge about it tomorrow and hopefully get out of it. But if not, then I'll try something else. I'll be very extreme.
You don't have any kids under 10? No kids under 10?
That used to work, not anymore. Okay, I actually would love to sit on a jury. I've never actually sat on a jury. I'd love to do it, just not in the middle of a semester. So, it is what it is.
Expert witness when you get paid $9 an hour?
Yeah. I want to see some evidence. All right, so today we're going to do definite integrals. So any questions over partial fractions or anything related to any of that? Yes?
So we did do one problem that had matrices, and I haven't got through all the homework yet, so I don't know if that pops up again. But I don't know. Yeah, I know you can't really tell us this, but I was suspecting. You must have showed us the matrices function for. So I would
well, I showed you how to use your calculator to solve a system of equations last class, right? Yeah. So when we did that, we set up that thing called an augmented matrix. That was matrices, basically. I don't know if that's what you're asking me.
Yeah, I guess I was like, was that something that will be seen later in the class, or is that?
We won't need to solve systems again in here, but as far as on the test, there could be a problem where having the calculator would be very useful and save you time.
Okay, got it.
Yeah.
So the final is cumulative, right?
It is cumulative, but mostly chapter 8.
Okay.
Yeah. So I wouldn't expect on the final to see a problem with partial fractions.
Okay.
Yeah. So you're gonna see it. You're gonna get tested on one time, and that's it. Yeah.
Gotcha. Cool. So forget everything we learned right after that.
You're gonna go to spring break. You're gonna come back, and we're gonna start over.
Are we doing series after spring break?
Not quite. We have to get through all the applications, volume, solids of revolution, arc length, surface area. Yeah, and then we get to chapter 8. All right, so we're good? Anything else? Recording, I'm not muted. All right. Okay, so this next part, I don't know if your professor covered this in Cal 1 or not. All right. I know in my Cal 1 I did cover this, so I'm not going to go into deep detail here, But there's something really important that I want everyone to be able to take away from this. So I'm going to cover just enough to make sure I emphasize that point. If you want any like more in-depth coverage of what I'm about to go through, then you'll need to reach out to me or something, okay? Yeah, just come to me and we can sit down and talk about it. So we are shifting gears now, okay? We are not talking about the techniques of integration anymore. Where'd it go? There it is. We're not talking about the techniques of integration. We, at this point, theoretically, have all the tools in our toolbox to find antiderivatives, right? We've got basic U substitution, integration by parts. We know how to handle trig integrals, sine and cosine to different powers. We know if we have square roots involved, there's these three forms, trig sub, and then we have partial fraction decomposition, and that's it. Those are our techniques. Now, we're going to see what we can do with all of these tools. And we go back to a very fundamental question, and it's tied into, ooh, squeaky. If you go to Cal 1, right, the fundamental problem in Cal 1 was if we go to some value x on a function, that we want to be able to find the slope of that tangent line, right? That's the Cal 1, the heart of the Cal 1 problem is finding that slope. And that required using the derivative. So now in Cal 2, we've got all our tools in the toolbox. What are some of the things we can do with that? Well, we go and we look at a function and we take that function and we start it at a point and we end it at a point. Let's call this first point A. Let's call the second point B. And what we are interested in here is seeing if there's a way that we can determine what the area underneath this function is. A, call it capital A. Can we figure out that area, right? So what is that area? And this, there's a historical background to this. Humans were trying to find the areas of circles, right? There was no formula. Pi r squared didn't exist, right? So we're trying to figure out how to do it, and we use different methods. And then what we figured is, you know what? If we can do it for a function, for any function, find the area underneath, then we should be able to handle pretty much any shape we ever need to find the area of. So the way that we attacked it, I have a picture over here to kind of give us an example. The way we attacked it is this. We said, what we can do is since we know the function, all right? Imagine that this function is given to you, all right? So that might be the function f of x equals x squared, or it might be sine of x, or I have a couple of examples here of functions that we could look at. Like right there, that's x squared, that's x cubed, that's a log function, this is another squared, here's an absolute value function, here's a cosine function. You know, there's all these different functions we could look at, but let's just do x squared. So let's say we have the function, and let's say we start it and end it somewhere. So I'm going to start here at the a is 1 and end it here at b is 5. And so if I wanted to approximate the area underneath the curve, so if I wanted to approximate, or sorry, not approximate, if I wanted to find that area right there, then what I could do is approximate it, right? Call this A. I could approximate it with rectangles. So you see this big gray rectangle? The area of that gray rectangle is however wide it is. Can you tell me how wide that is? A minus, or B minus A. It's B minus A, right? So 5 take away 1, that would be 4, right? And how tall is that rectangle? 20. Well, what are we doing? We're taking that top right endpoint, right? That's how tall it is. That means we're plugging 5 into the function, which we know the function, right? And I told you it's x squared, right? So 5 squared is 25. So this is 25. So what's the area of that rectangle? The whole rectangle? 4 times 25? 100, right? So see that area right there? 100. That's the computer giving me the area of the rectangle. Now, is that area of the rectangle the area of the blue? No. It's got a bunch of shit that I don't want, right? But it is an approximation, not a good one, but it is an approximation, right? So this right here, this area, 41.33, that is the true area. So we're pretty far away from the true answer, aren't we? So then what we do is we say, okay, instead of doing that, what we could do is, instead of doing one rectangle, we could do 2 rectangles. And what I mean by that is, instead of going the entire width, let's cut it in half, figure out that and this, and those should be the same width, right? How wide are they here? These are 2 here, and this is 2. This one has a height of 25, but this one has a height of 3 squared, 9. Okay, so the area of this one would be 2 times 9 is 18, and then here 2 times 25, that's 50, and if I add these together, I get 68, right? And that's a better approximation, right? Because I have less error, right? I have less error. This region that I was including before is no longer there, right? Got it? And then how could I get a better approximation? Just more rectangles, right? Just do more rectangles, more rectangles, more rectangles. And the more rectangles I use, the better my approximation gets. So I'm going to have the computer do this. And what I want you to do is just pay attention to this number 68. Here's 3 rectangles. Here's 4 rectangles, right? You see that number is getting closer to the true area? But each time I do it, what's happening is that the width of the rectangles keeps getting smaller, right? So now they're only how wide? 1 each, right? And you have to figure out the height at each of these endpoints, but your error, the part that's above here, just keeps getting smaller and smaller and smaller. So if I could keep going, right, like this, if I could keep going, what's happening is that those rectangles, each one of them, right, each one of them, this width, right, this width right here is shrinking, right, shrinking. It's becoming infinitesimally small if I keep going, right? The more I go, the smaller they get, but the better my approximation gets, right? And the idea is that if there's a way to put an infinite number of rectangles in here, an infinite number of them, then I would have the true area. But there's a problem with that, because if you go and you let the number of rectangles become infinite, what happens to the width? It approaches 0, right? So we have this idea of a limit. We say, okay, what I want to do is I want to take the limit as the number of rectangles goes to infinity. And then we know in Cal 1, we know how to calculate limits, right? And this limit, if we could somehow set it up, which we do these things called Riemann sums, which I'm not going to get deep into today. If we could somehow take the limit, then we would get closer and closer and closer. And eventually, if we let it go to infinity, we would actually head to the true answer, right? So let me back up a little bit. It's a little bit too much here. What I want you to see here is that each one of these rectangles, if I take one of these, okay, just one of them, and I look at it over here, the height of that rectangle is just the function's value at this right endpoint. I'll call it x, right? Would you agree that's how tall that rectangle is?
Yes.
Yes? And then the width of the rectangle, the width is the same for each rectangle, right? It's the same for each one. And that's just how much x changes by as I move across. All right, I'm just going to jump across each one of these by the same amount. So we call this delta x, change in x. It's the change in x, and it's constant throughout every rectangle. Right? And so I take that, and then what I want to do is I want to add all those rectangles up together, right? So I want to take the sum. All right, show of hands, how many of you have seen this notation? Yes, most of you. Okay, a little bit. This just says you're going to add up a bunch of things. And what you're going to add up are the areas of all these rectangles, right? The areas. So how would you find the area of this rectangle right here? You take that and multiply by that, right? Width times height, or height times width. So that would just be, I want the sum of all of these rectangles, right? I want the sum of all those rectangles. Just trying to get you to see like a mathematical notation for the idea. I want to add up the area of the rectangles, each one of them, right? Each one, add them all up. And so we somehow want to incorporate the limit. So we're going to take the limit of this as the number of rectangles goes to infinity. Again, this is not precise mathematical notation. It's more of us just getting a general idea of what's happening. I want to take the limit as I let the number of rectangles go to infinity of the sum of all of those rectangles. And if I could do that, then I would get the true area. So whatever this is, this should be equal to the true area A, all right? The true area of this. So for a long time, humans, when they wanted to find areas under functions, what they would do is they would try and see if they could come up with some generic formula that would give you the area here. And then they would actually do sums and add up. They would add up like n rectangles. They would do arbitrary. They wouldn't do like 4 or 5 or 100. They would they would come up with a formula for n rectangles, and then they would take the limit as n went to infinity, and then they would try and grind that out and get an answer. And it's a pain in the ass. I know some of you have done Riemann sums, right? And they're brutal, all right, if you have. And so we sat there for a long time and we tried to figure it out. And what we determined is that there's a connection between this answer and the antiderivative of that function. There's a connection between the two. And I'm about to give that to you, but before I give you that to you, I want to show you this right here is a lot to write, right? This right here is a lot to write. The limit as a number of rectangles go to infinity of the sum of this times this. So what we did is instead of that, we said, let's just use a different notation. Instead of using this sum, we're not going to use sigma again, because we're not doing sigma, we're doing the limit as we let this go to infinity. Let's use this symbol instead. That symbol. And that's where that symbol came from. We've been using that symbol, haven't we? But we never talked about where it came from. It's actually like an S that's been stretched out. So it's sum, right? It's like stretch it out. That's a sum with a limit in front. That's basically what that means. And what is it that I'm adding up? So I'm taking a sum of what? And I'm going to have infinitely many? These things, right? So I have in here f of x times, now this delta x, because we're going to have an infinite number of them, that width of a rectangle goes down to basically 0, so it becomes infinitesimally small. So instead of writing delta x, we write dx. So I want you to now look at this notation that we've been using, and I want you to see that this means we're going to be, taking the sum. It's going to be an infinite sum. Infinite sum of what? This is the height of a rectangle times the width of a rectangle, right? The height times the width. So height times width, add it to height times width, add it to height times width, add it to height times width, add them all up. How many of them are you going to have in there? An infinite number of them. That's what this notation represents, all right? There's one more thing, though, that I have to add to this notation that wasn't there before, and that is wherever we start, we have to know where we start and we have to know where we end. So this is always A and this is always B. So what we do is below on the bottom of this, we put an A, and on the top we put a B. And that gives you basically what we call the limits of the interval. So yes.
I know I've asked this before, but it's still kind of hard to understand dx. So why is dx our width for the rectangles?
Why is it? Well, we want to find the area of a rectangle, right? So we can call this quantity right here, this width, we call it anything we want. Delta x is usually the standard notation for it. It's just a change in x. But if that delta x becomes infinitesimally small, then we use dx instead of delta x. It's what lets you know we're taking the limit as this thing heads to 0, right? Then it becomes dx. I'm not sure if that's answering your question.
It's just because like the d and dx isn't arbitrary like that.
The D in dx?
Yeah, because like we can choose like any symbol, but like I guess I don't really know how to word it.
So, I think it's dx because it's in respect to a change in x, yes.
Mm-hmm. Delta x, right?
So like, you have delta x, and it's becoming so small that it's going to be 0. So if you're going to write that notation, you can write it as dx because it's talking about the difference of the x, change in x, I think.
When we write delta x, we're just saying that there's a change in x and it's fixed. Okay, so like if I say, you know, what's delta x between 1 and 2? What's this delta x right here? Is 1, right? Delta x is usually reserved for when that is never changing. It's always 1, 1, 1, 1 the whole time. The width of each rectangle is 1. But if I'm going to let the number of rectangles go to infinity, then that delta x is no longer fixed, right? It's becoming infinitesimally small. So it's changing in a limit, it's getting smaller. So to distinguish that from delta x, we use the notation dx.
I guess I'll ask this question because I think in a roundabout way it might answer mine.
Mhm.
When we take the derivative, it's represented by d over dx.
Yes.
What does that top d alone mean?
It means you're doing a differential operator. You're doing the differential operation. So when you write d dx, you're differentiating with respect to x. So if I do that right there, what this means is I'm taking the limit as h goes to 0 of f of x plus h minus f of x over, I'm going back to Cal 1, like definition of the derivative. That's the definition of the derivative. That's what this means,
Yeah.
right?
Yeah.
So the d is just telling you you're doing that operation. This right here is connected. It's this right here. The dx, here's another way to look at it, and we're going to go too far off the tangent. If I take a function like x squared, and I go to some place x, right? Now, if I just nudge x to the right a little bit, now I'm over here, right? I just nudge, just infinitesimal, right? So now this is x plus some little dx. Now if I go up here, I've changed my height. My height's changed, right? My height has nudged up, that's dy. So if I nudge by dx, I'm going to nudge up by dy. The x squared dictates how fast my y changes, right? My x is going to change by the same amount. If I nudge a little bit here, but depending on where I am on the function, my dy may be different. So if I'm trying to find the tangent line there, I'm taking the ratio of that divided by that. dy over dx is your slope of tangent line. Yes?
And I always thought that we call it dx for the change of x over, like because in physics or when it's dx usually just changes time, which is always going to be like either like 1 millisecond or 1 second.
Yeah, I'm just saying that dx here for us, the way I want us to, the takeaway from this is that today when we walked into class, like if you hadn't seen this before, this stuff, then this meant for us to go find the antiderivative, right? That's all it meant. Go find the antiderivative, and we have a plus c at the end, right? And the notation for us is this is the function we're going to find the antiderivative of, and the dx was keeping track of the variable for us so that when we made any substitutions, we could keep track of everything, right? That's what it's meant to us so far. But now I'm telling you that this notation actually comes from this idea of trying to find the sum of these rectangles. And so we want to look at this, this notation now as this is the height of the function, this is the the height of the rectangle, the width of the rectangle, and this tells you to add up an infinitely many of them between the interval a and b. That's what this new notation is, all right? So with that notation, all right, I have this all in the notes. We have formal, where is it? We have formal words for this. Let me get to it. So in the notes, I go through Riemann sums, and I show you, if you're interested in that, you can try and read through that. But let me get to the final crux of everything here. Yeah, I'll give you that next. That's going to be our next note. So when you have this notation, this will be A, right? This is the area under the function f on the interval AB. Okay, if we can compute this somehow, and I haven't shown you, like I already told you, this sum is hard to do by hand. It's nearly impossible. Some functions we can do it for, but for many we can't. So, but we know what this notation represents. This number on the bottom is called the lower limit of integration. And then this is called the upper limit of integration. And your answer here, your answer should be a number, right? It's not going to be some function plus c anymore. This should give you a numerical value because it's representing the area underneath that curve, right? So things are similar, but they're different, right? So this is, all of this is called a definite integral. What we've been doing before this was called an indefinite integral because your answer was some function plus c, so it was a family of functions, right? There was an infinite number of functions that would qualify. Now, we're not getting a function as an answer, we're getting a definite answer, right? A numerical answer, which is why we call it the definite integral. So indefinite, answer is a function plus c. Definite integral, you normally get a numerical answer which represents the area under the curve. So mathematicians, dealt with this, trying to do Riemann sums, trying to figure out is there an easy way to do this? Is there an easy way to find that area? And then finally, we figured it out, all right? And we made the connection. And the connection is summarized in the fundamental theorem of calculus. And by its name, right, the fundamental theorem of calculus, calculus is a pretty big subject, right? This is the fundamental theorem of this subject. And that is the connection between the derivative and the antiderivative, or a function and its antiderivative, and how it all ties together. So there's two versions of the fundamental theorem of calculus, and I'm showing you what's called the evaluation theorem, which is the second version, and this is the one that we use the most. The book talks about the first version if you're interested in that one. Again, that's more of an office hours thing. This is the one we're going to use. So this says that, look, if you want to find the area, that right there represents the area under some function, right? Have some function, starts at A, ends at B. If you want to find the area underneath that, okay, if you want that, all you have to do, just look at this part right here. All you have to do is this. You have to find the antiderivative. So little f is the function, capital F is the antiderivative. Find the antiderivative and evaluate it at the two endpoints, and you've got your answer. That's it. Now we're not proving this theorem. We're just going to accept it and use it. So let me show it to you in an example first. Again, I think a lot of you have seen this. So for example, let's take that function f of x equals x squared on that interval 1, 5, which was the one I showed you the picture of, and let's find the area. Under it, yep. All right, so all we have to do is this. Go 1 to 5. We put the function here, x squared dx. This is the height of the function. This is the height of the rectangle, width of the rectangle. Multiply them together, you get the area, and we're going to add all those areas up between 1 and 5. According to the fundamental theorem of calculus, this should just be the antiderivative, right? The antiderivative evaluated at the two endpoints. What is the antiderivative? 1/3 x cubed, right? So what we normally do is right here at this step, we have this intermediate step. This step right here, what it does is it allows us to write down the antiderivative. It's like a placeholder. It just gives us an opportunity to just write down what the antiderivative is. So my next step is to write down the antiderivative, 1/3 x cubed, and then we put a bar next to this. We call this the evaluation bar, and we put the 5 up here and the 1 down here. So that just allows me to write the antiderivative down. The bar tells me I'm not done, I need to do something now. So now I'm going to plug 5 into this. Notice in the formula, the b, which is the top number, goes in first. Then you subtract the a, plugged in. So I'm going to take something and subtract something. So 5 into here first, 1/3 times 5 cubed. And then I plug in the 1, so 1/3 times 1 cubed. And this should be 125 over 3. 5 cubed is 125. 1/3 of 125 is 125 over 3. Then over here, this just turns into 1/3. And so my answer is 124 over 3. Pardon? What?
Oh, never mind. It's not reducible.
Oh, I didn't hear what you said. 124.
So did that test all possible values between those, or did it only test?
What the fundamental theorem of calculus allowed us to do just now is take an infinite number of rectangles and add them up.
And would that be the actual?
That's the true area.
Okay.
That is the true area. In fact, if you do that on your calculator right now, you're going to get, what, 41.333333, which coincides with what I had shown you in that when we did this, right? Look at the answer. The actual area was 41.333. That was because I had the computer actually do that for me. All right? So, yes.
So when we're trying to find the area under a curve, we have the upper limit and then the lower limit.
Yes.
By having those, is that the reason why we don't have a plus c? Is because it's defining?
That's right. Okay, so I'm glad you brought this up. Let me... Wait, we do have a plus c, but... Let's say in this step, I did this, right? I said 1/3 x cubed. That's the antiderivative. But it could have been plus any number, right? So what if I would have done plus 7? Fine. If I evaluate that 5 and 1 here, does that change our answer?
Well, yeah, I would think.
Change the final answer.
Does it change the final answer?
Because the 7 subtract.
The 7s are going to subtract, right? So you plug in 5 into this, you get 1/3 5 cubed plus 7. And then over here, you get 1/3 times 1 cubed plus 7. But see, when you subtract that plus 7, and then this minus goes through and the minus 7, they kill each other off. And that would happen anytime you have any number there, right? So this can be any number you want it to be, so what's the most convenient number to use? 0. So when we do the fundamental theorem of calculus, we usually just put the antiderivative plus 0, so just this by itself. I'm not sure if that's what you were asking.
Yeah.
Okay.
Another question. So you know how like if we just have 1x, we just write it as x. Is there like